Okay, so now we get into more complicated situations. So that's not complicated enough, but it gets even worse, right? So let's go back to our simple filling a tank. Now, it was already complicated to begin with, right? We have something filling into here, mixing into here, and it's eventually coming out. Now the situation is, well, what if we have an alternative? Meaning, what if we have two different pumps pouring in water? And after a certain amount of time, the other pump goes in. So this ends up being an actual piecewise function is, well, after a certain amount of time, let's say, so after 5 seconds, or the first 5 seconds, this pump is pouring water. Then after 5 seconds, this pump, part B, floods in, right? It's like this closes, and now this floods into the water here, and eventually, pours out the same process. So we actually get a piecewise function based off the functions themselves, right? We have one particular function going in, and after some amount, one other function going in. And again, we can get far more detail, right? We can have 4 pumps, 3 pumps, but it saves the process as it splits up the time in parts and eventually gets into here. But the question is, how does this look like? And so now this is far more difficult than just simple differential equations situation, even if it's just scenarios. How does this actually apply? Okay, so for this type of problem, it actually looking like this. Okay, it's the basic format where this is the amount of water going in, so valve A, and we'll just call it from 0 to 7, and this is the amount of water going in after 7 seconds, so this is valve B. Okay, so here's our situation. Okay, so the question now becomes, how much fluid or how much salt is in at a certain amount of time given a situation, right? So this is a little farther going backwards. So the best part is, just like everything in calculus, if you can go one way, you can go the other way. Meaning, a lot of times we took the derivatives and going forward, but now we're going backwards. We're taking straight integration. Okay, so when it comes to these type of problems, mixing problems, where it's a piecewise function, we're going to learn a new type of format. And actually, a lot of people believe this is far easier than everything we've learned so far, because it actually works for a lot of stuff we've done before. And this method will be called the Laplace transformation. So just like the name says, we're going to be transforming our function to something easier and then going backwards. That's pretty much the plan itself, right? You could think of it like polar coordinates, where this is something more complicated to, so for example, if you have the double integral of something like this, which is not so fun to do, or, let's say with a sine e to the x or e to the y here, this is very complicated to do. If we convert this to polar, it makes it much easier. This is just r, but yada, yada, yada. But you kind of get the picture. And then we just work our way backwards, right, to go back to the x and y. So kind of the same process here is using this Laplace transformation. Is we're going to transform our ridiculously weird function into the Laplace transformation, do everything there, and then just work our way backwards itself. So in other words, take the inverse of the Laplace. Okay. Now it sounds complicated, but it's actually not as bad as you may think. That's the best part. Okay. But first, let's define what in the world a Laplace transformation ends up being. Okay. So our transformation is going to look like this. Okay. So we're going to transform f of t into capital F of s. Right. That's our transformation. So from t to s. And it goes like this. So it's an infinite integral, so indefinite integral of this. So the key thing is, remember that it goes to infinity because our bounds are literally just from 0 to infinity. This is always a constant term, and this is the function we're actually transforming. Okay. Now remember, it's a simple integral. It's one integral, not double integrals. So remembering s is going to be a constant term. Okay. So let's formally actually introduce it, this definition, besides just talking about it. Okay. So let f of t be a function on the basically open integral from 0 to infinity. So the Laplace transformation of f to capital F is defined by this integral. Okay. Again, s is constant. So t is the only thing we're actually integrating. Okay, so again, s is constant, so we just treat it like a normal number, like 5, 10, -2, things like that. Okay. All right, so the domain of f of it is all values of f for which the integral exists. So sometimes we have to define the actual domain itself based on what we actually find. Okay, and that's usually if we're dividing, what is it going to be over, higher, things like that. The Laplace transformation of f is to know about, again, both capital F, or the more common term is the fancy L with the brackets of f, where again the fancy L represents the Laplace for L itself. Okay. Usually you see it far more in detail with this one instead of that one. They usually give Laplace far more credit than it is just a simple little f here. Okay. So all we really want to do is how do we go from one to the other, meaning using our definition, how do we just create a Laplace transformation given arbitrary functions before we solve for crazy amount of stuff. So again, all we want to do is be able to just do some transformation of some constant functions. Okay. So first we're going to start for mere basics. What if it's just a constant with like 1, 5, or 1,000, right? So let f of t equal 1. Okay, so if I go by our definition, so the Laplace transformation is going to equal to the integral from 0 to infinity of e to the negative st times 1 dt. Okay. Well, it's times 1, so it's just going to be itself. Okay. So now this is, we've got to go back to a little bit of pre-cal, or not, calculus. Remembering infinity. So we can't really actually take the integrals of a value to infinity. So what this definition is, it's actually taking the limit. And I'll just pick an arbitrary number. So let's say n goes to infinity of the integral 0 to n. Because we do actually need bounds, okay? Even if it's an arbitrary variable. Okay? So most of the time when it comes to these transformations, you're going to be using a lot of u substitution. So let u equal that. Take the derivative. That's negative s, so we don't have that. So we divide over. So this ends up being integral of negative 1 over s e to the u du, which is just itself. So negative 1 over s times e to the u power. Evaluate at 0 and n. And again, we're taking the limit of this entire thing. Okay. All right, so plug in each one individually. So if I plug in n for t, remember it's just for t. So this ends up being negative 1 over s plus e to the negative sn minus. Plug in 0 in for t, so that goes, this ends up being a whole just 1, because e to the 0 power is just 1. All right. And it's not supposed to be times. What am I doing there? Times, okay. So breaking this down, positive. So now if I take the limit as n goes to infinity of this, so if this goes down here, so this is taking the limit as this goes to positive infinity, gets super, super small. So that basically goes to 0. So it's just 1 over s. So our domain is all the numbers pretty much greater than 0, because again, it's defined to be 0 to infinity. So it's just anything greater than s is perfectly fine. Okay. So now let's go a little bit more difficult, right? So the nice thing is it works for any constant. So if it was 100, it would do the same thing as a constant. So you just bring it to the front, and you would have 100 here over s. You know, kind of the same template we have here. And you'll see that going forward as well when we talk about the tables. Okay, same process. So it's going to be the Laplace transformation. And since we already know it's going to be limit, I'm just going to write that down. And again, now a is a constant, so s and a are constants this time. Okay, so we're going to use the property of exponents here. When you multiply, you technically add the powers together. So it would be e to the negative st plus at dt. So again, use substitution. Everything on the inside. Du would be negative s plus a dt. Okay, so I don't have that. So again, this is just a constant, right? I don't know what this constant is, but it's just a single constant, as if it was the same thing as this s here. So I can actually just divide this whole thing over. And there we go. So now we get the basic same process we had over here, where it's just this is on the outside of the integral e to the u power. So same process, so just e to the negative st plus at over this, evaluate at 0 and n, and again we take the limit at the very end. Right, so plugging in capital N for t, I'll keep it a negative. And all this becomes 1. Now, this process here, let's talk about it. Let's make it a little easier. What happens if I factor out a negative n? This ends up being s minus a. So in the same process now, this whole thing will come down here because it's a negative power to make it positive, and we have the same situation as we did earlier right here. So as n goes to infinity, this is 1 over a very large number, which means it just goes to 0. So really it just depends on this process here. Alright, so make this a little easier. Minus minus makes positive. So this ends up being s minus a. Alright, so again, not too bad, right? Just a little bit of work remembering the limits. But what if we have this now? Okay, sine of bt. Oh boy. Okay. So this is going to equal to the limit of n goes to infinity of e to the st times sine bt dt. How lovely, isn't that? Okay, so you have actually no choice but to use partial, what's the word? Integration by parts, integration by parts to do this process. Or, the nice thing about Laplace transformations is a lot of stuff is pretty much constant, just like series was and Taylor series. Same thing applies for Laplace transformations. So if I go on this table, sine and cosine are already pretty much done for me, and we actually proved this one. right? It was 1 over s. So all of these are constants already, already done for us. So let's just use them instead of using, our good old integration process and our techniques. So since we're dealing with finding Laplace of sine of vt, which is exactly that one, and doing the long way around, doing the good old limits and the integrals, we'll just use this. So the Laplace transformation of sine of bt will equal to b over, is it s squared plus b squared? Yep, s squared plus b squared. So much easier than have to do all of that work. Okay. So, speaking of that process now, let's now do a piecewise function, which is the key thing of why Laplace is actually very useful. Okay. Now, we're doing each individual case. So this is when f of t is equal to this, this, and this, right, going forward. Okay. So using our process, we know that f of t equaling 1, that Laplace transformation is going to be 1 over s. And we can actually use that process the same thing here. Okay. Now, the question is, how do we do that? Okay. Now, this is going to change a little bit because of our balance, and that's the most important thing. So we can't actually use all of this, meaning unlike over here where we had unbounded situations where it was just a function of 1, we have bounds, right? Remember, because the Laplace goes from 0 to infinity, but that infinity has a bound of if we have one, and we actually have 2 bounds here. One will go to infinity, meaning this one will go to infinity. Okay. However, the other 2 actually have bounds. So, for instance, now we actually have to do the work, but it's going to look something like this. It's going to go from 0 to 5 of e to the negative st times 2. And then we just integrate that, same forth. So we did this earlier, right? So I'll put the 2 on the outside. So let u equal this process. du is negative s, so just 1 over it. So, and it's going to be the same. So it's actually 2, or I'll put negative on the front, s times e to the, this process evaluate at 0 and 5. So now we actually get something a little different, but it's the same process here, because if we plug in 5 everywhere, say t, this now becomes negative 2 over s times e to the 5s minus, if I plug in 0, so all it gets 1, negative negative make a plus 2 over s. So this part is this portion. And so now the next part is when f of t equals 0. So that's bounded between 5 and 10. And it's going to be e to the negative st times 0. Well, the best part of being multiplied by 0 is just going to be 0. Well, the integral of 0 is literally just 0. Right? That's the interesting part. So it actually ends up being nothing. There's no Laplace transformation there. Okay. And then finally the last one is this one has the endless bounds. So this one's going from 10 to infinity. So take the limit as n goes to infinity of e to the st times e to the 4t dt. Okay. So again, we kind of did this earlier, right? We just did a is equal to 4 in this case. So this is again the integral. Okay. Now, we can try to do our shortcut here because we're actually dealing with this one. But we got to be a little bit careful, right? Because we have a bit of a situation when it comes to S and A. Okay, so it's going to look like this situation a bit. Okay, so in this case, our A value is going to be 4. Sorry, 4. So our A value is equal to 4 in this process. But we're going to have a little bit of a sticker because, again, these correspond from 0 to infinity. And that's a problem. We don't have 0 to infinity, we have 10 to infinity. So we actually have to do the work here, unfortunately. So this is the only one so far. We could have just a little shortcut because we're bounded itself. Okay. All right, so again, we did this earlier, so I'm not going to go too far into depth. So this ends up being the limit as n goes to infinity of I'll do it this way. So again, if you're wondering where I'm getting this information from, it's exactly here. Kind of following the same template. This is what I got. So n is, and then just plug in 10 in the respective slot. Gives us that. Not 0 in this case, so it just doesn't get you 1. And that's the problem. So again, as n goes to infinity, this ends up going to 0. So we just get this process. Okay. So the complete Laplace transformation is this and this put together. So and then plus this. There we go. And just for be the safe side, we have our domain, so it can't be 0, right? And since s has to be constant, that's positive. So we know it can't be 0 because we'll get z's on the bottom. This will only be 0 when we have 4, or 4. So usually we say s is greater than 4 would always work. Just to be on the safe side. All right. So what we just did here is exactly this theorem. Is basically if we have functions or 2 or more different functions put together, the Laplace transformation of all of them will just be the sum of each individual case. And this is where I get this part from here, where the Laplace transformation only exists if s is greater than a. And since a was 4 to begin with, we say the constant s has to be greater than 4 to make this true. Because if it's less, then we get a negative, which is no bueno, right? We always want everything positive to our domain. So we're forcing everything to be positive. Okay, so knowing this aspect now, let's actually use our tables. Okay. So the question is, how do we use the tables? Okay. All right, so we're going to split this up. So we're going to do each one individually. So we're going to do Laplace transformation of 11, and then Laplace transformation of this 5e to the 4t, and then again for the last one, negative 6 sine 2t. Okay. Okay. So we're going to match each one to its respective here, right? Now the best part is it's multiplication or constants in the front. So in other words, I can rewrite the Laplace transformation of 11 to equal 11 times the Laplace transformation of 1. And that is what this theorem at the very bottom says. If I have a constant here, I can literally just bring it on the outside and then multiply by it. So in other words, it's very nice because eventually when we hit the next portion of summations and all that fun stuff, it follows the same template. And then come, power series and all that fun stuff. But we'll start there. So all I do is go to my chart. The Laplace transformation for 1 is here, is 1 over s. So it'll be 1 over s times 11. So it's just 11 over s. That's this first part. And I'm going to do the same thing for each individual case. So bringing this, so Laplace transformation of 5e to the 4t is equal to, well, 5 times the Laplace transformation of e to the 4t. So now I go down here. This follows this template where a is 4. So therefore it's going to be 5 times this part here. So 5 over s minus 4. All right, and then finally the last one. So in this case, I'm going to factor out the negative 6 and just deal with the sine of 2t. And now I go down here. Since it's sine, it follows this template right there. So in this case, b is equal to 2. So again, just follow the exact same process. So it's going to be the b, so 2 times negative 6 is negative 12 on top, over s squared plus b squared, so that's going to give you 4. So now all we do is put everything together. So this Laplace transformation of this function here is going to be the sum of all 3 put together. So again, where s has to be greater than 4. So once you get the hang of it, it's actually kind of nice, especially if we could use tables, it's even better itself. Okay. So now let's try one more. So find the Laplace transformation of this function. Okay. All right, so we have a lot of stuff happening. This is a little bit more complicated than we had before. Okay, so let's just first break it down. Okay. All right, and where is my, here it is. Okay, let's see. So we have t and e, so right here. Okay, so in our case, in this situation, we have 2 different letters we got to identify, a and n. So a is always next to the, it raised to the e power, the n is always the t power here. So in this case, n is equal to 2, and we have a equal to negative 3. And this is how it's going to look there. Okay. And then this 5, I'll just bring to the outside. Okay. Like that. All right, so if we just follow our template. Now, just in case you guys forgot, this is a factorial, right? So it's that number times everything before it. Or you could just leave it as a factorial. It's perfectly fine. So in this case, it's going to be 5 times n factorial, so 2 factorial, which is basically just 2, all over s minus a, so that gives you plus 3, raised to the n plus 1 powers, which is 3. So this is the Laplace transformation of this part there. Okay. Now I'll do the same process here. So it looks like it's going to look like the last one we have here of cosine. So we need two different letters, A and B. So in this case, A looks like it's going to be 12, and B is going to be 8. And again, I'm going to bring this negative to the outside. Like that. And now I just follow exactly what we have. So the top is going to be S minus A. So S minus 12 over, again, S minus 12 squared plus B squared. So our B squared in this case is 8, so 64. All right, and then we just put this together. So I'll simplify this, it's just going to be 10. And again, where S has to be greater than now 12, since 12 is the bigger of the two A's. Right, so last theorem and definitions here applied to the piecewise functions is, basically like the example we did over, you could just split up each individually. However, one key thing is when it comes to exponential growth and exponential order, we won't get too much in detail in this class, but the key thing for the exponential order is any power or any function that's less than or equal to some power, we can actually find that one as well. This is a little bit more complicated than we're going to be dealing with in this class, but again, it's just nice to know that we can have bounds. Okay, so if m is, or the function t is bounded by a function or two, we can also do the same stuff. So again, a little precursor to series and Taylor series going forward, since we could do error bounds and all that fun stuff as well. Okay. But the key thing we're going to deal with is if f of x is a piecewise function, continuous on 0 to infinity, so basically interval from 0 to infinity, and the exponential order a, then the Laplace exists for such a value, which we proved earlier, right? So when it came to our piecewise function. But again, it's nice to know and give you an actual theorem based off that.